Inside the Qutub Minar complex in Delhi stands a massive column of iron. It weighs over 6 tons and stretches nearly 24 feet into the air. If you leave a raw piece of iron outside, it immediately begins reacting with oxygen and moisture to form iron oxide. It rusts. A modern steel structure left completely exposed to the elements without protective coatings would eventually flake away to dust. Yet this structure has stood outside for 16 centuries. It has endured thousands of torrential Indian monsoon rains, and the metal remains completely rust-free. It is also incredibly dense. In the 18th century, artillerymen fired a cannon at it. The heavy iron ball scored a direct hit, but the pillar didn't shatter. The weapon barely left a dent. This survival is a microscopic anomaly. The iron itself contains a structural quirk that directly challenges the rules of how we manufacture metal today. To see how that happened, we have to look back to the Gupta period, roughly the 4th century. The ancient smiths who built this didn't have blast furnaces. Instead, they used a technique called solid-state reduction, burning charcoal to heat iron ore until it formed a spongy, porous mass. To construct a massive pillar from those small pieces, they forge-welded them. They heated the lumps until they were glowing red, stacked them, and violently hammered them together by hand to squeeze out the liquid waste. There is one crucial difference between this ancient process and how we make steel today. Modern blast furnaces use lime, calcium oxide, to chemically strip away impurities from the liquid metal. The Gupta smiths did not add lime. This text details the chemical makeup of ancient iron. Without lime, the smelting process created what is called phyolitic slag, a byproduct that trapped unusually high levels of an element called phosphorus right inside the iron matrix. If you work in a modern foundry, you treat phosphorus as a contaminant. It makes steel brittle and prone to packing, so contemporary manufacturers spend a massive amount of energy scrubbing it out of their products. The ancient Indian smiths couldn't remove it. That specific technological limitation is the exact chemical accident that keeps this metal intact. When rain hits the pillar, water and oxygen interact with trapped phosphorus. Instead of forming flaky red rust, this catalyzes the moisture into a dense amorphous barrier. As it repeatedly dries and wets, it locks into a crystalline force field known as iron hydrogen phosphate hydrate. These published chemical formulas show exactly how the iron and transient oxides react with phosphoric acid. This sequence creates an insoluble shield over the raw metal underneath. The metal literally grows its own armor. The more the environment assaults it with oxygen and water, the thicker and more protective that crystalline skin becomes. The engineers who crafted this didn't design it for its current location in Delhi. It was originally erected hundreds of miles away, outside the Udaygiri cave temples, set up to precisely align with the sun on the summer solstice. Centuries later, medieval kings uprooted the massive monolith and dragged it here to the Qutb Minar complex to serve as a high-profile trophy of conquest. It has sat outside ever since, outlasting almost every modern steel equivalent. Today, the modern industrial steelmaking process aggressively purifies raw iron, baking out the phosphorus to create uniform, highly predictable building materials. Material scientists have spent decades analyzing this specific pillar, trying to replicate its corrosion resistance. They found that our pursuit of absolute chemical purity actually eliminated the exact element that gives this ancient iron its resilience. By manually hammering porous iron filled with what we now consider impurities, 4th century artisans achieved something modern blast furnaces cannot. Their handcrafted chemical accident produced a self-healing structure that easily outlasts modern steel.